Tommy Hall. He's a mathematician, a part-time mountaineer, and likes to post beautiful mountain pictures on Twitter. So if you like beautiful mountain pictures, follow him. And he describes himself as a fine chap, whatever that is. And he's going to talk about the symmetry of things. So let's all give a warm welcome and applause to Tommy Hall.
Yeah, thank you very much. It's nice to be back in Berlin for clojureD. It's one of my favorite conferences, and I get to talk about two of my favorite ideas, which is really fun. So you might know me as that Tarsier guy from the internet. There are three of us, I think, with very similar avatars. We occasionally get confused for one another, but I am the one that posts the mountain pics roughly once per day. Where we're aiming for this talk is a wonderful book called The Symmetries of Things, but I want to talk about another one of my favorite ideas, which I first saw inside the structure interpretation of computer programs. So a few years ago I did a thing to port SICP to Clojure, or the highlights of it to Clojure. So one of my favorite highlights is a thing from Peter Henderson, where he embeds in Lisp a way of describing Escher pictures, which is rather nice. So the first half of the talk is essentially how Henderson uses a deep embedding of into Lisp of a language for describing pictures, and then we move on to different kinds of symmetries as per the book previously referenced. So to get started, there's a picture called George, and we can start describing drawings of George. So the draw function, and we say beside George, George. So beside places two pictures alongside one another. There's a function called flip horizontal, which will flip George horizontally. So actually that's more fun than I realized. Okay, so George is waving now. George is beside the version of himself flipped. Oh, no, I was having too much fun then, sorry. There you go. So we can describe these pictures, and we can put one picture beside another. We can flip a picture horizontally, etc. And we can now say below, beside George, the flipped horizontal version, and then beside George, the flipped horizontal version, and one is below the other. So we've got this language for describing pictures and combinations and transformations thereof. And so we can start building up a language for talking about them. So we say draw the rotated version of George. So we've got a rotate function. I won't spend too long on this. I think the SICP distilled chapter is actually quite a good treatment of all this stuff. So I'm going to move fairly quickly so I can get on to the newer stuff, the symmetries of things stuff. So we can rotate pictures 180 degrees by rotating them twice. So what's really nice here is we're using the normal means of combination provided by Clojure. So we can make functions that reference other functions, etc. And we can also use recursion, which is going to help us draw these sort of infinite Escher pictures. So a function called right split, which recurs into itself. So draw the picture and the right split of the picture on top of one another, and then recurse until n is 0. So we've got this idea of, so I can say the right split of George going 4 deep, and that's the picture it gets. So right split takes the identity, i.e. the picture itself, and then creates 2, recurs twice, into 1 less, and then if it's equal to 0, you just draw the picture. So that's what we get. We get 1 person, then 2 people, then 4 people, then 8 people, etc. So we can, because we've got this embedded in Clojure, we can do things we can do in Clojure. It's just functions, so we can recurse and we can do stuff like this. So now a function called corner split, which splits it into 4 pieces. So I said up, right, top left, bottom right, and corner to try and describe them. So we've got this, again, the identity function, so the image is going to be in the bottom left corner, and then we're doing the up split, right split, and corner split of the same image. So we're getting close already to our Escher picture now, which is nice. So a quartet now, below. I think I've actually, since I wrote these slides a while ago, I call the function above now rather than below, because it was more mnemonic about the relation between the pitches. So if you do look now, actually I've just remembered, I call it above in the SIC feeder still thing. So we've got a quartet of pitches, which says put pitcher 1 beside pitcher 2, and then pitcher 3 beside pitcher 4, and then put one on top of the other. Yeah. So we got a different pitcher type there. So we can say, again, because we've got functions, we can use higher order functions, which is functions that take functions as arguments and return functions. So we have a square of 4 function, which takes 4 functions and returns a function that takes a picture and then draws it. So does that make sense? A little tricky. So we've got here the top left is a function, so we call that function on the picture. Might be identity, might be flip, might be rotate, whatever. And then the top right function, and we're basically assembling them into a square. So you pass in 4 functions, and then I will return a function that takes a picture that draws in a square those 4 functions. So because we've got this deep embedding in Clojure, we're able to do our methods of combination from within Clojure to describe solutions to, I was going to say solutions to our problems, but really in this case it's draw pretty pictures, isn't it? In the general case, you use it to solve your own problems by expressing solutions in the domain-specific language. So here we go. Draw, again, this function we don't know anything about yet. Square of 4 of the identity, the vertically flipped version, the horizontally flipped version, and the rotated version. So we're saying this is a higher order function, so the return value of this, I'll highlight it, the return value of this is a function which takes a picture, which we've then told it to draw, and we've passed it in the picture George. We don't know what the picture George is yet, or what that means, and we don't know how this draw function works yet. So we're able to describe things without necessarily understanding how they're implemented, which there's a nice symmetry with, there's a nice correspondence with the symmetry book that we're going to talk about. So is everybody getting me so far? So far, so good. But we still don't know how to draw anything. We haven't actually said how to draw anything. We've got a function called draw that we use to describe, or we use to draw these pictures we've transformed, but we don't know what a picture is or what a drawing is. So, and we're using a library called Quil, and I think someone else mentioned it already today. It's a 2D drawing library in Clojure that's very nice. Quil lets you draw lines. So once you can draw lines, you can draw pictures composed of lines. And what I really, really love about this example is this whole blurring the distinction between code and data. Pictures in this embedding are procedures themselves, they're functions themselves. So the really neat trick from Henderson is pictures themselves are functions. So that's kind of nice, but what kind of function is it? So it's a picture is a function that takes a frame as an argument, and it takes the picture has the responsibility of drawing itself inside that frame. So a frame is a rectangle, possibly skewed somewhere in the 2D plane, and you pass a picture, which is a procedure, a function, a frame, and it is responsible for drawing inside it. So our first picture is just a frame painter. So you pass it in a frame, and it just draws the outline of the frame. So this is probably the first thing I can demo to you. Ooh. Oh, damn, I've revealed my surprise. Not that. We can draw the frame painter. I think John Hughes spoke about this yesterday at the other conference, which I didn't go to. I wish I did. Is he here? No. Okay, I think he described that waiting for the printer to print it out. And what I really like, so in my day job I do a lot of DevOps stuff, so I'm used to sort of slow feedback loops. Yawn. So what I really like about Quil is you can just evaluate as you go. So if I call the frame painter on this first frame and the second frame, then it draws around the frame. So that's our first picture. Segment Painter takes a list of line segments and just draws them all together. I'm not going to spend too long on that. But we can now say Segment Painter, and we hand it a frame. Now, diag is another picture, and we say draw the diagonal inside the frame. The diagonal is a Segment Painter with this line segment. So it's going from 0, 0 to 1, 1. So the trick again that Henderson adopts is you draw pitches inside the unit square, so inside from 0 to 1 on the x, inside 0 to 1 on the y, and anything you draw inside that unit square, the square with sides length 1, anything you draw in there gets expanded into the rectangle, into the frame. So if we go and draw things like a half and then a circle around it or something, it would appear in the center of the frame. Does that make sense? Cool. So the draw function then is just a procedure that takes a picture and just draws it in the whole window. So the draw function takes the picture and calls the picture, which is a function, on the frame that represents the entire window. So what that draw function we used before, you now know. You now know how to draw lines, and you can draw segments and stuff. And I'm not going to talk about this, but we can use this higher order function again to have picture transforming functions, which then we can use to create a flip vert, flip horizontal, and rotate function. But we can then do beside and below in terms of these transformations as well. And beside and below is interesting. You've got two pictures you want to draw inside the one frame. So the strategy is, well, we're going to split it in the middle. The left frame is going to be this other picture, and the right is going to be a transformed version of the picture. And then we're going to say, draw in the frame the left picture we've done, which is going to draw in the left half, and draw in the frame the right picture, which only draws in the right half. So we're using higher order functions to make true all of our promises from before. So beside and below and above, etc., can all be created from these functions. Above is actually just the rotation of a beside, which is also quite nice. You could kind of rotate things and then flip it back, which is nice. So one thing I like about this is all pictures based on lines. So all the transformation is based on pictures that are composed entirely of lines. So if we want a different procedure type, so it turns out that Quil has an image drawing function. So if we can honor that interface of a picture is a procedure that takes responsibility for drawing itself within a frame, then we can actually, all of the things we've done above, below, all of that was based on the idea of pictures. So if we can do a different picture type where we actually can draw an image inside that frame, then we can allow images and the same two frames, but with the image painter inside it. So Bruce is an image painter. So we have an actual JPEG that we load in, and then we create an image painter out of it, which then allows us to pass a frame like before. So this procedural abstraction, this Bruce is a picture, which is a function that takes the argument of the frame. So image painter is using some Quil stuff with a transformation matrix, which sort of translates, shears, and scales the frame. So if we can do that, then where we had the square limit before of I forgot to do the square limit of George. So let's see this. So we can do the square limit of, it's just slow. I gave up too soon. Oh God, I've asked it for 10 deep, that's why. Okay. And I forgot to undraw those. So those two frames shouldn't be drawn. So this is going to take a little while again, so I need to be patient. I'm not very good at slow feedback loops, as you can tell. OK, so we can draw it for George. And for a conference-specific one, I grabbed the logo. So we can recurse and do that. So that kind of allows for some Escher pictures to be drawn. We're roughly halfway through the talk, which is nice, almost like I planned it. And then, but a whole class of Escher pictures is then describable, and we can take the square limit of this angels tile I've got, which is done such that it can be combined with the reflection of itself, etc. But that only allows this kind of square symmetry, the reflection. So other Escher pictures, for instance, exhibit different symmetries. Which is where we get onto our second book, which classifies all of the plane symmetries. So I'm going to go through this. The book starts with this beautiful idea, which is kind of counter to what mathematics normally does. So mathematics normally, you build up this edifice slowly and prove everything, and in the end, you've got the result you want. There's a wonderful property of this book where they keep punting the explanation to the next chapter, to the next chapter, to the next chapter. So it says, we start with a problem, enumerating symmetric patterns. We introduce tools for solving the problem, and then complete the enumeration. So you're done, except there's a second problem. Why do the tools work the way you claim? And then they solve that problem with some tools, but then have to present the mathematics that supports the tools. So every chapter ends with a, where are we, and what do we need to prove next? Oh, well, if this thing's true, then we can carry on. Oh, but why is this thing true? And there's this really nice pattern of punting off the sort of foundational things to the next chapter all the time, which is rather nice. So in order to sort of enumerate all of the plane symmetries, if the shape's finite, it must fix a point. So the idea of a symmetry in general, is that you can transform the shape and have it look the same. So here is mirror symmetry, or what they call kaleidoscopic symmetry. So here they've got 1, 2, 3 mirror lines, and if we reflect in those lines, the shape is maintained. Because it's a finite shape, it must fix a point. So we star n dot means it's n-fold, I keep going to say mirror symmetry, n-fold kaleidoscopic symmetry fixing a point. And you can have as many of the mirror lines as there are natural numbers, so there's infinitely many of those. And the other type of symmetry for that fixes a point is rotational symmetry. So you can turn that wheel 1, 2, 3, 4, 5. So it has 5-fold rotational symmetry. They actually call it gyrational symmetry. And that's the flag of the Isle of Man. So that has 3-fold gyrational symmetry, fixing a point. So there's infinitely many of those. There's also for so-called frieze patterns, which is repeating patterns. And this is some examples from architecture. You can imagine these being done with like a roller, so it is the case that they're kind of equivalent to the surface of a cylinder. I found when preparing this talk that you can get Escher cookie cutters, which is quite nice. So if you can go arbitrarily long, as much as your oven will accommodate, I suppose, of like a nice repeating pattern and make Escher cookies, which is nice. So again, back to our Escher thing that we're aiming at. You can see where the yellow heads come together. There's that 3-fold kaleidoscopic symmetry. And similarly, where the red heads come together. And so the tails of the yellow thing. So Escher's clearly informed by this idea of kaleidoscopic symmetry. So to take a simple example from wallpaper. You've got a mirror symmetry here. You've got a mirror symmetry going the other way. And if you kind of mark out all the points of this mirror symmetry, you wind up with a hexagon around the flower. And actually 1, 2, 3, 4, 5, 6 different mirror lines going through it. So you'd say that is like a 6-fold kaleidoscopic symmetry at that point. But there's also a 3-fold one in the corner of the or between the flowers. And there's also a twofold one here. So there's this idea that you have these repeating patterns where if you follow all of the lines of the mirror symmetry, the kaleidoscopic symmetry, you carve the space up into these triangles, but then actually you can rebuild the whole shape from just one triangle, right? So the shape of that triangle determines the whole of the shape and what the contents of that triangle. So here is one of the plane symmetries. I'll give you a little spoiler. There's actually 17 different ones. And this is, you would call this star 632. And the convention is that you go descend numerically. So from this triangle, you can recapitulate the whole picture. And I'll show you where I am with my... I'm not as smart as Henderson, so I've got a not as good embedding of the problem. I've actually flummoxed myself in not being able to reflect it beyond the original, beyond this hexagon, so excuse me. So if you take the... I'm only reflecting lines as well, so if I draw an extra line in the triangles, which takes the midpoint, and you may remember if you do the same for every edge and connect it to the halfway along the opposite edge, or every edge halfway across between the opposite sides. God, I didn't say that very well, did I? So yeah, if I connect those three up, then we've got our symmetrical pattern, and the median of the triangle is found. So I haven't got as nice as an expression as the Henderson one, because I'm reflecting the same triangle several times, but I don't have a good way of expressing, well, outside of that, like reflect again. So if anybody's interested in helping me out, that would be awesome. So that's the last of the demos, and I'm afraid, well, no, I'm not afraid. I'm going to tell you that from now it's all mathematics, but it's good mathematics, I promise. So the other type of symmetry we've seen is this rotational symmetry. So there are several points here. There are some points that are mirror symmetry, so you can probably see them, fairly obvious. I hope you can see my big cursor. So there's a mirror symmetry line going here, here, and here, and as you can probably guess, remember this would be like a threefold kaleidoscopic symmetry, but there's also a rotational symmetry in this kind of empty space here. So that's not by a mirror, but I've got a picture that zooms in a minute. Can everyone see the sort of rotational symmetry here? So we've got threefold kaleidoscopic, threefold gyroscopic. So this is like 3 star 3 symmetry, this one. And there you go, so 3 star 3. And that triangle determines the entire shape of the plane, or the drawings on the plane. So just like the book itself does, I'm going to introduce a theorem called the magic theorem, and whereas they punt it off to the next chapter, the proof of it, I'm going to punt it off to the book. So there's a sort of twofold punting there. So the magic theorem states, if you write down the symmetry, the pattern, it always adds up to $2. So even though you don't know you don't know why the magic theorem's true, you do know that if I'm going to tell you this fact that all of the symmetries of the plane, when described using this notation, all add up to $2. So you don't know what this circle means, but you know we're only allowed that circle. We've spent our $2. So there's one symmetry that is that circle. Yeah. If we have 2 of these, that equals a half, so it means 2 should be in there. Does that make sense? And all the ways you can make $2 from these prices are how you can tile the plane, or rather describe a symmetry of the plane. So it's fairly easy to go through and pick them all out, but it turns out there's 17 of them. You know and could recognize probably all of these, because these are mirror ones. Remember so there's different triangles. This one is a square. 2, 2, 2, 2 is 2 mirror lines, or 2 kaleidoscopic points of order 2. And there's 4 of them, so that's basically a rectangle and then reflected round. The other 3 are triangles and then reflected round. We've seen some of these. The only thing you don't yet know is what does this mean and what does the cross mean. So I'm going to briefly show you what they're to do with. And one thing we haven't mentioned, if you've done symmetry stuff before in school, we've done rotational and reflectional symmetry. There's also the concept of like translational symmetry, isn't it? Just simply moving something. And there's a concept of glide reflection as well as the other one. So that's what these symbols represent. So just quickly, this is just straight translational symmetry. This is our wonder ring, it's called, the blue circle. So the problem, not the problem, a fact about the book is that it doesn't use the standard terminology, but there's some novel stuff in there as well, and I find the way it brings everything together is really, really nice. So the so-called wonder ring is saying that you've got a straight translation between that. You could take the plane and just shift it. And this one is, I think the correct terminology is a glide reflection. But, a glide reflection. But they call them miracles because it's all of these patterns, the non-polygonal ones, all divide the mirror lines. Divide the region into infinitely big slices. So this idea of a miracle is where you got 2 corresponding points. That's kind of a translation, but also a reflection, but not described by a gyroscopic point. And they're so-called miracles or mirrorless crossings. And then you have the final one here is so there's 1 mirror line and 1 so-called miracle, which is star cross, which in our cost was this costs 1, this costs 1. So you can have 2 of those according to the magic theorem. So I hope that's whet your appetite for what is a fabulous book. I hope maybe you've got a better intuition for me about 2D transformations in Quil. I've got another version of a project where I actually have an image in HTML5 canvas that I actually do just copy and blit into itself to do the mirror rotations. I haven't found a good way to that's why I wanted to go half on the Henderson one, because it's a very rich and fruitful embedding. I haven't yet found it for rotations, reflections. So if anyone's curious and wants to get involved or has done something similar, please do let me know. So I've got a few links about stuff. And do you have any questions? I have 4 minutes for questions.
Yes, questions. Everyone's speechless.
Well, thank you for your indulgence then. Oh.
I might ask a magic question if you have a magic answer. So I have a question which I don't know if there is any answer, but how to use the symmetrical property you described to get to bijective data transformation? I mean, data transformation that works in both ways.
Yeah. I'm not sure I understand the question, to be honest.
Like you have a JSON structure, you transform it in some XML,
yeah,
and you wanted to transfer it back using the same code.
Oh, okay.
This is a kind of symmetry.
Yeah, a bijection formally means that the function's injective and surjective, doesn't it? Which means you can undo it. The inverse exists. But I don't know how.
What I meant precisely is to create the invert of the function using symmetrical properties without programming the inverse.
Ah, got you. I've never seen anything like that to automatically do the inverse function. I think the mathematical property of bijection just means that it exists, and that the domain and codomain are they correspond. So I don't know any way to automate that. I would punt on it being equivalent to solving the whole halting problem. That's always a safe bet.
Thanks.
Cool, thank you. Well, thanks for your indulgence.
So any more magic questions? No, then thank you, Tommy.
Cool.